Okay, so welcome to these lectures on Lie symmetries in general relativity. So I hope that everybody can listen me. Okay. Yeah. Okay, so I'll start from the basic concepts, mainly from scratch. It involves different areas in mathematics, mathematical physics, and so on. So basically in the first lecture, I'll give you the notation, basic definitions, so that we can move on to the use of these symmetries in general relativity. So this area uses concepts from differential geometry, Riemannian geometry, Lie algebras, mathematical physics, because we're mainly focusing on the use of these symmetry methods in general relativity, basically the exact solutions from the field equations of general relativity. So I will first like to talk about the relevant books. So the relevant books, this is not an exhaustive list of books on this subject, but the books I have mostly used for these lectures. These are some of them. The first book is one of the most cited book on the exact solutions in general relativity. So it's in fact, it's a catalog of the exact solutions in general relativity, and it appeared in 2003. It was the second edition. I think earlier one was a bit old, maybe 10 or 15 years old, but the latest one came in 2003. So it gave the basic concepts on symmetries, also the classifications of the solutions in general relativity of the Einstein field equations, different schemes for the classification, different methods, and some basic concepts. The book at number 2 by Graham Hall is perhaps the most relevant book for these lectures. Its main emphasis on the symmetry methods that are used in general relativity, the theorems, the main results I will be talking during these lectures are mostly available there in that book, Graham Hall. And in fact, some of those I was discussing with Graham about 3 days ago also. So this book is also relevant for these basic ideas in general relativity. The book 3 and 4 are the basic books for general relativity, basically, the text one. The 3 is Misner, Thorne, and Wheeler, perhaps the most cited book on the subject. It's taught everywhere, and almost all wherever they teach gravitation or general relativity, they mostly use this. This is standard reference book. The book at 4, Hawking and Ellis, is actually 3 is a bit long. So 4 is shorter than that, and I like its presentation very much, particularly the diagrams and things like that. They explain the things in a beautiful manner. It's not as long as the reference at 3. It's longer. Number 5 is Chandrasekhar's book on the mathematical theory of black holes. So it's actually the application of the concepts of geometry, Riemannian geometry, and so on in the construction of black holes. So after reading this book, one is convinced that black holes are basically mathematical constructs. So this is a mathematical object. So this is a wonderful book. Number 6 is the Riemannian geometry by Eisenhardt. It's a bit old, one of the earlier books on the subject. And then the 7 is also by Eisenhardt. It's also an old book. This on the groups of transformations used in geometry and so on. So this list is actually not a list of references. The references are given at the end, but this is the core books that can be used to study the subject. So this the research papers and other books, they are mentioned at the end as a reference. So as I go on with the lectures, actually I'm developing this on this file, the tech file. So if anybody will be interested, I'll make them available, these lecture notes also. Okay, so the first thing I'd like to talk about is the space-time. Actually, the results and the techniques and methods I'll be talking about, most of them are applicable in any space, in any dimensions. But I am starting this with the space-time because we will be mainly interested in the application of those results in general relativity. So in general relativity, the basic concept is space-time, so 4-dimensional space-time. And as we go on with the results and theorems, I'll mention there that they can be extended to n dimensions, some of them. So n-dimensional manifolds, and even Euclidean manifolds, Euclidean 4-dimensional spaces also. So the results, many of them are, general results for any manifold. But because the emphasis of this course is the application of all these results to general relativity, so therefore we will mostly come to the 4-dimensional manifold, and those manifolds will be Lorentzian manifolds, basically. So the notation, the main purpose in the introduction is to set the notation. So Mn, you see here, is the manifold, an n-dimensional manifold, or M4 we can say if it's a 4-dimensional manifold. And Gij is the metric tensor that actually measures the distance on these manifolds. The coordinates, so this space-time, as Wheeler says, is basically the arena of physics. It's the set of all events going on this space. So space and time, events mean time, 1 dimension from the time and 3 dimensions from the space. So in Cartesian coordinates, for example, we will write them as t, x, y, z, or in spherical polar coordinates, we'll write them as t, r, theta, phi. So if it's 4-dimensional, we will be using these two notations for defining our metric tensor and other things as we go on. So here I'm talking about the flat space and the curved space also. As I mentioned earlier, many of the results are applicable both to the flat as well as curved spaces. And we will mention if there are any differences in those theorems. But as I said earlier, mostly we will be concerned with the curved space of general relativity, the Riemannian geometry. Okay, so this xi is the notation, therefore vector. So x0, x1, x2, x3. So here we will mostly, these indices will be running from 0 to 3. Although in some books you will see them as going from 1 to 4. So it depends on the books. So here I will follow this notation from 0 to 3. This GAB, the metric tensor, is a second rank covariant tensor, symmetric tensor. So GAB is equal to GBA. It's symmetric in its indices, lower indices. The general Riemannian metric is given by equation 2. So this is the most general metric on any manifold, whether it's is flat or curved, Euclidean, non-Euclidean, whatever. So here, yeah, first I should mention this, that if an index appears twice in a term, and if it appears twice, it will be usually one in the lower position and one in the upper position, in the covariant position and the contravariant position. We will assume that there is a summation on this index. So I will not use the sigma notation for summation. It's called Einstein summation convention. So whenever there is an index like here, A, so there's a summation, and B, there's a summation on B also. And the summation goes from, it depends on the dimension of the manifold. For example, if it's 4-dimensional, Lorentzian, it will go from 0 to 3. So this will be our notation that we have used in this equation number 2. So this is the Riemannian metric. ds square is the square of the distance actually for any space. So this notation we will be using throughout these lectures. Okay. And then a comment about the signature. So if this is 0, 1, 2, 3, the time and 3 spatial coordinates, so the people use 2 types of signatures, either plus, minus, 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 or minus, plus, plus, plus. So this is a Lorentzian manifold, 2 types of signatures used, but we will be using one of them. In flat space, for example, flat space time Minkowski, if we want to write the basic the flat space, the basic space-time, ground level space-time for general relativity in Cartesian coordinates, we will only have diagonal terms -1, +1, +1, and +1. Maybe it will be better if we move to the blackboard. So for the GAB, I'm saying there, yes. Okay. So to show you all the components. So this is what is called the Minkowski space, sometimes written as M4. So this is this Minkowski flat space in Cartesian coordinates. Yeah, remember it's in Cartesian coordinates. And if we transform it to spherical polar coordinates, this will be, I'm not sure. Yeah, in spherical polar coordinates, and we will be mostly using spherical polar coordinates. So I should mention here that this will become this r square 0, 0, 0, r square sine square theta. So here the coordinates I am using are t, r, theta, and phi. And here is Cartesian coordinates t, x, y, and z. So this is because it's not given in the matrix form there, so I thought it's better to at least once put them on the board because we will be using this later on. Okay, so the metric tensor is symmetric and we can find its inverse also. With the metric tensor is denoted by the covariant indices TAB, and its inverse is given in the contravariant form. So GAC. So equation 4 defines its the inverse of the metric tensor. GAC the contravariant and GCV in covariant form. And if their product gives us the Kronecker delta AB, which you know is 0 when A is not equal to B, and it is 1 when A is equal to B. So this denotes this gives us the inverse of the metric tensor. Okay, so this Equation number 5 is essentially what I have written on the board, but here you see one constant C also. So sometimes the first coordinate T is written as Ct, where C is the speed of light. So C is multiplied T, so that now the dimensions of all the coordinates are the same. So now it gives it the dimension of length Ct. So but C is a constant, so we'll mostly ignore it. And there is another notation also used in some books. They write Ct as a new time, capital T. So here also we can multiply this with C. So for a fixed velocity, if we fix our velocity, the units of time will actually measure the distance. So time and distance become the same thing for a fixed velocity. And for fixed constant velocity, we usually use the speed of sound C, speed of light. I'm sorry, speed of light C over here. So in the coming matrix or notations, you will see that we will mostly ignore this constant C, the speed of light. These notations, I'll talk about this later. These are called natural units or gravitational units, where we put C equal to 1, and some other constants also we put them equal to 1. So these called gravitational units or natural units. Okay, so the basic tensor of this our subject is the metric tensor. There are also some other objects and tensors that are developed from this tensor, and they are very useful. Actually, they are essential for studying this subject of general relativity. So those tensors which are constructed with the help of metric tensor, now I would like to talk about them. They're not only tensor, there are other objects also. For example, Christoffel symbol, it's not a tensor, but it's a very useful object which is developed from the metric tensor, its inverse and its derivatives partial. So Christoffel symbol is written by this gamma, capital gamma. And there are two types of notation used in the books. Some people write it has this gamma, A, B, C. So there's something with 3 indices, A, B, C. And some books use this in this bracket also, this curly bracket, or even like this also. Okay. And the Christoffel symbols are actually of 2 kinds. They say the Christoffel symbol of first kind and the Christoffel symbol of second kind. The first kind is given by this equation number 6. They're all written in lower position. So the notation is that if we use an index in lower position, we call it as a covariant index. And if this is our convention that we will be using, and if the indices are placed in an upper position, they are called contravariant indices. So in the first kind of this Christoffel symbol, you see all the indices A, B, C, they are put in the lower position. Now this comma means the partial derivative. So this is partial derivative. This G, B, C, comma, A means let me put it right on the board, because it will be used later. So it's I want to make the notation clear. So this is, for example, G, B, C, comma, A means the partial derivative of G, B, C with respect to XA. So this is the coordinate A. And as I mentioned earlier, this XA, if it's a 4-dimensional manifold, this is the notation that is used. So this is the comma means this partial derivative with respect to A. And the second kind of the Christoffel symbol is given in 7. It's one index you can see one index is in upper position and 2 are in lower position. And here this GAD with the upper indices is the inverse of the metric tensor. Okay. So this is the Christoffel symbol actually in 7 that we will be using here. This only this, not the first kind. And we actually, most of the books call this as the Christoffel symbol because this is used mostly in general relativity and in this curvature structures of general relativity. So we call this as the Christoffel symbol given by this 7. And this is symmetric in lower indices. So 9, the equation 9 states this fact that ABC is equal to ACB. There's some other combinations of the first kind also. For example, this ABC plus BCA, we add these two, which is clear actually from equation 6. This is ABC, we construct another Christoffel symbol BCA, and we add these two, all the terms will be cancelled, and we will be left with 2 times GAC comma B, and 2 will be cancelled with 1/2, and we will get this identity number 10. And from 6 and 7, actually, the Christoffel symbol of the first kind can be used. The first and second kind, they can be related with the help of this metric tensor. Another use of the metric tensor is that it is used to raise and lower the indices. So for example, if we want to, as I mentioned earlier, with the notation is that if an index is in lower position, we call it as a covariant index. If we want to take it to upper position, convert the covariant to the contravariant form, we will multiply this with the metric tensor, and actually there will be a summation going on. So in 11, for example, you see this is the Christoffel symbol. Sorry, said if we multiply with the metric tensor, it will lower the index from upper position to the lower position. Okay. So on the right hand side, you see G is in upper position. If we multiply with this metric tensor, we get an index in a lower position. There's a summation on G, and this is converted into a completely an object with all the indices in lower position. Similarly, if we want to raise an index from covariant to contravariant, we will multiply with the inverse of the metric tensor. So this is an important use of metric tensor that we will be using in this lecture. That I repeat it, if we want to bring an index from an upper position to lower position, we will multiply with the metric tensor. So the index will, from the covariant contravariant form, it will be converted, it will be taken to a covariant position. And if we want to raise an index, we will multiply with the inverse of the metric tensor, and it will raise the index. So this use of lowering and raising in indices is also an application of the metric tensor. And I again, let me repeat that this Christoffel symbol is again a symbol, it's not a tensor. It can be checked why it's not a tensor, because it does not transform like this. The tensors have transformation laws, and the Christoffel symbols do not transform according to those laws. So it's not actually a tensor. It looks like a tensor. It behaves like a tensor. The summation we will be applying on these indices will be just like tensors, but it's not a genuine tensor. It's a symbol only. It's basically a combination of the partial derivatives and the inverse of the metric tensor. So it's a combination of these things. Now, I just talked about the partial derivative, but there's another derivative in Riemannian geometry that's used, and that is called the covariant derivative. It's in special cases, in flat Euclidean spaces, for example, the covariant derivative reduces to the partial derivative. So if the space is flat, if there is no curvature, and if there is no curvature, this means that all the Christoffel symbols will be 0. If all the Christoffel symbols are 0, then there is no difference between covariant derivative and the partial derivative. So after making this thing clear, the difference between two clear, The partial derivative we will be denoting it by this semicolon notation. So the covariant derivative will be used, we will be using the semicolon. So differentiate the partial derivative from the covariant derivative. Partial derivatives are denoted by commas and the covariant derivatives are denoted by semicolon. And this is the definition of in 13. The first term is the partial derivative. So this is AB is a vector, any vector. Its covariant derivative B semicolon A is written by this. So you see the first term is the partial derivative and the next term Christoffel symbol is involved. So this Christoffel symbol, there is a summation over the index D, AD. So this is, I repeat what I've said earlier. If this term is 0, second term is 0, then actually the covariant derivative is the partial derivative. And when it is 0, if the space is flat, in Euclidean spaces, when you use the differentiation, the ODEs and PDEs on Euclidean spaces, you use partial derivatives and don't use the covariant derivatives. Why? The reason is that you're working on flat spaces over there, if that is the case. And the Christoffel symbols are 0. So the second term is 0, and covariant derivative reduces to the partial derivative. There's no difference between them. So the question 13 gives the definition of a covariant derivative of a covariant vector. 14 gives the covariant derivative of a contravariant vector. The vector is, the index is in upper position. The difference, you note that here the second term comes with a plus sign. Whereas if it's in a covariant position, if it was a covariant vector, the second terms come with the negative sign. And now you can see these two were the definitions in the case of vectors. If it's not a vector, if it's a tensor of rank 2 indices, then there will be 2 extra terms on the right-hand side. The first term will be the partial derivative and then 2 extra terms on the right-hand side involving Christoffel symbols. Now the Christoffel symbols, they're coming with plus sign or minus sign, depends on the position of those indices. If both of those indices are in a contravariant position, these 2 terms will come with plus sign. If those indices are in covariant position, then these 2 terms on the right will come with negative signs. And if it's a mixed tensor, we call a tensor if some indices are in upper position and some in lower position, some in covariant, some in contravariant, then some terms will be positive and some terms will be negative, as you can expect. So if it's a mixed tensor of rank 2, the covariant derivative will have 3 terms in all. The first term will be the partial derivative, another term with the plus sign involving Christoffel symbol, and third term with the negative sign, again involving the Christoffel symbol. The 15 is a very general formula for a covariant derivative of a general tensor of a large number of indices, A to B and C to D. Note that the first term is always a partial derivative, and it does not involve Christoffel symbols. However, the other terms will involve Christoffel symbols, and the plus sign denote that they are for the upper indices, and then there will be some terms with negative signs, and they will be with the lower indices, basically. Now, the metric tensor is a special tensor, as I mentioned earlier. Its covariant derivative is given by 16. It has 2 indices in lower position. So the first term will be the partial derivative, and the other 2 terms will involve the Christoffel symbol, both with negative sign, both with minus sign, because both the indices are in lower position. Okay. And again, I would like to stress the fact that if the space is flat, then there is no difference between covariant derivative and partial derivative, because the extra terms will be 0 and the covariant derivative reduces to the partial derivative. They become the same thing. covariant derivative. And it's also called covariant derivative because it increases the rank of a tensor. You can see that if we start with the vector, if for example with one index, the covariant derivative, it becomes another, it becomes a tensor with the two indices. So it is also called covariant derivative because it increases the covariant rank of a tensor. So if the covariant rank of a tensor is 2, for example, and we take its covariant derivative, it becomes a tensor of rank 3. You see? So the number of components will increase. It's a much bigger tensor now. The large number, the number of, like in 13, we started with a vector of one index and it becomes a tensor with two indices. So if we have a tensor, say, with two contravariant indices and three covariant, it's called 2-3 tensor. If we take its covariant derivative, it will become 2-4 tensor. Okay, maybe I should write this fact on the board. So if we have a tensor with LK, L is the upper indices, the contravariant indices, and K is the covariant indices, and we perform covariant derivative, covariant differentiation. It will turn into a new tensor of rank K L plus valence L K plus 1. So here the rank, its rank was L plus K, the number of contravariant indices plus the number of covariant indices. After covariant differentiation, now its rank is L plus K plus 1. So the covariant differentiation transforms a vector or a tensor into a new quantity. Okay. So you can see the screen. Okay. So we will denote this covariant derivative with a semicolon and partial derivative with just a comma. And there's the metric compatibility, which says this thing that the inverse of the covariant derivative, inverse of the metric tensor, if we take the covariant derivative, it gives 0. Now, as I mentioned earlier, we can construct new tensors by using the metric tensor and the Christoffel symbols and so on. And the most important tensor in this theory is the Riemann curvature tensor, sometimes called the Riemann Christoffel curvature tensor, or just the curvature tensor. Some books call it as Riemann Christoffel tensor. I'm not giving its complete derivation. Actually, I'm not giving the derivations of these, but it will take a long full semester course. I'm only giving the definitions and how they can be constructed by using the tensors and objects that I've defined earlier. So 19 gives the definition of the Riemann curvature tensor. It's a tensor of rank 4 and usually written like this. One index in upper position and 3 indices in lower position. And right hand side it gives the definition. So you see it involves the Christoffel symbols, their products, and their partial derivatives. And these Christoffel symbols, as you've just seen, involves metric tensors, their inverses, and their partial derivatives. So this becomes a very complicated and highly nonlinear object, this Riemann curvature tensor. And actually this measures the curvature of any space, any manifold. This actually gives you the mathematical test whether a space is curved or flat. So if this tensor, this is a genuine tensor. Note that it is defined in terms of Christoffel symbols, which are not genuine tensors, they are just objects, a combination of partial derivatives. But Riemann tensor is a genuine tensor. And if this tensor is zero on some space on manifold, that will be a flat manifold. And if it is non-zero, then we say that the manifold is curved. There is a curvature. So this is a measure of curvature of a manifold, any manifold. So this is what I've written in the next the sentence. And in one situation where this can be zeros, I mentioned earlier, the space, if and on a space all the Christoffel symbols are zero, then obviously this 19 will right hand side will be zero, and this will be a flat space with no curvature. Now this is mostly written in this notation: one index upper and three indices in lower position. But if we give it another notation, for example, we can study its properties also, and its properties they are useful for our for the discussion that will be coming. That we know these algebraic properties, the algebraic symmetries. So algebraic symmetry means that symmetries of the indices. Okay. So for example, in lower indices, if I bring the upper index to the lower position A, B, C, D, this is symmetric, skew symmetric in the first two indices. Let me write. So to see the symmetries of this tensor A, B, C, D, this is minus R, B, A, C, D. So this is skew symmetric in the first two indices. This is skew symmetric in the last two indices. And it is symmetric pairwise. I mean, if we write or CD, AB. It automatically goes to that mode when I. Okay. Okay, so these are the algebraic symmetries, the symmetries of this Riemann tensor. That in the first two, sorry, in the first two indices, it is skew symmetric. In the last two indices also it is skew symmetric. But if we take the pair and they put AB in the position of CD, it is called pairwise symmetry. Or block symmetry. It is also called block symmetry. Okay. Another property satisfied with these Riemann curvature tensor is the second equation. This is called Bianchi's first identity. A, B, C, D. So now this is a symmetrizer bracket, which means that we can take the cyclic permutations of this, for example, BCD plus RACDD plus RADBC. And this is equal to 0. So this is another constraint that this tensor satisfies. And this is called Bianchi's first identity, because we will come to the second identity also. So that is why this is an algebraic identity. The algebraic identity involves only the changing the position of the indices. So these are important symmetries that are followed by the Riemann curvature tensor. From the Riemann curvature tensor, we can construct other tensors also. All these tensors will be used in the later discussion. That is why I am giving their definitions. Okay. So if this Riemann tensor in 19, if we represent A and C indices with the same notation, if we give them same notation, that is, they will be subject to Einstein summation convention. We also call it taking the trace, like we take the trace of a matrix. So if A and C becomes the same index, then although it looks like a rank 4 tensor, it will actually become a tensor of rank 2 in 20. You see, there is a summation over A. Now, if there is a summation over A, which means only B and C are two free indices. A is now a dummy index. It's called a dummy index. So the free indices are only two, B and C. So it actually becomes a tensor of rank 2. So from a tensor of rank 4, by applying this summation convention or contraction, this concept is called contraction of tensors. In this contraction, if we contract two indices, you see that it is converted into a tensor of rank 2. So it's no more a tensor of rank 4. This tensor of rank 2 is also a special tensor, and it is called the Ricci tensor, after the name of the Italian mathematician Tolvino Ricci. Actually, Ricci has a contribution, a lot of contribution in this subject of this Riemannian geometry. There's so much contribution that initially this subject was called as the Ricci calculus. And one of the first books, perhaps the first book on this subject, the title of that book was Ricci calculus by Schouten. So it's a big contribution by Ricci on this subject. So the question 20 defines the Ricci tensor. I repeat the fact that it is constructed from a tensor of rank 4 by contraction, by summation convention, by taking the trace. So this is a technique which reduces the rank of the tensor. If we have any tensor, we apply contraction, it will reduce the rank. Okay. The technique we will be using, that the one index should be in upper position and the other should be in lower position, and we apply summation convention and it reduces the ranks. For example, it was a rank 4 tensor, Riemann curvature tensor, it is reduced to a tensor of rank 2. Now note that it's a tensor of rank 2, we can again apply contraction to reduce its rank. But in order to apply that contraction, we first will have to raise that one index in upper position. If we raise the one index in upper position and then apply the contraction, it will become a tensor of rank 0, which is a scalar. So 21, this is what we have done. The Ricci tensor, which was of rank 2, we again applied contraction and it become a scalar, which is called Ricci scalar. So both these quantities are very useful, and you will see in the coming discussion how useful these are. So this is the Ricci tensor of rank 2, and this is the Ricci scalar. Now, as we have obtained this Ricci tensor from Riemann tensor, we can write this Ricci tensor from the definition of Riemann tensor also. This definition 19. So you see, so if we apply that contraction we were talking about on the right hand side of 19, this rank 4 tensor will become a tensor of rank 2. And this is what we have done in equation 22. We applied that contraction on the right hand side, and this is another, we can define a Ricci tensor in this way also. So this is the definition of the Ricci tensor. This is useful actually in working out these components. We have, when we have some manifold, some space-time given to us, and we want to calculate this Ricci tensor, this is a useful definition. So the Ricci tensor is also symmetric. So RBC is equal to RCB. It's it's a symmetric covariant tensor. Another tensor that will be used in the discussion is the stress energy momentum tensor. It's the long name of this tensor, the stress energy momentum tensor. But usually in the books or research papers, people don't write its full name. They shorten the name. They call it the stress energy tensor or energy momentum tensor, or so on. And sometimes they just call it as the matter tensor. Because it actually denotes the matter content of the space, and if it's a space-time, the matter contents of the space-time. It describes everything about the matter, energy, the distribution and motion of matter, the contents of the space. They are given, they are denoted by this tensor, and we denote it by TAB. And actually, this is the important answer when we will come to these Einstein field equations that we will talk about later. So the TAB is defined in a contravariant form. Both the indices are written in the upper position, but we can always bring those indices down, as I mentioned earlier. For one index to bring down, we multiply it with the inverse of the metric tensor. And if we have to bring down both the indices, we'll multiply with the two inverses of the metric tensor. So now you see, this is a summation over beta and gamma. And this is the indices are now in a lower position, in covariant position. So this is writing the energy momentum or stress energy tensor in the contravariant form. This is a covariant form, and we can write it in the mixed form also. Equation 25 gives this in the mixed form, one index in upper position and one index in lower position. An important property of this tensor is that it is divergence free. Divergence, this property is very useful in mathematical physics and in the discussion that will come, that its divergence is zero. Actually, this gives a conserved quantity. We will see later and talk about it more later, that conservation of matter, that it can neither be created nor destroyed during the motion, is denoted by this factor, that its divergence is free. And this divergence, we have denoted by the covariant derivative. So the covariant differentiation that we have taken of this matter tensor. And it's also symmetric. So the Ricci tensor was also symmetric in the lower indices, and this matter tensor, the energy momentum tensor, is also symmetric. TAB is equal to TBA. And this is an important property of both these tensors that will be used in the construction of the later tensor we will be talking about. Okay. Now this is the last tensor I would like to talk about, and that is the Einstein tensor. Einstein tensor is obtained by using the tensor that we have defined earlier. Actually, we defined those tensors earlier because we wanted to define this tensor, Einstein tensor. And this is the second Bianchi identity. Again, I'm not giving the derivation of this here, but the Bianchi second identity. Bianchi's first identity, this is Bianchi's first identity, which is an algebraic identity, no differentiation involved in it. Bianchi's second identity involves differentiation. B, C, semicolon, D equal to 0. Now again, this is a symmetrizer bracket, which means that we will take the different combinations. So BC semicolon D plus R CD semicolon D plus R BBC semicolon, sorry, A BB semicolon C equal to 0. So this is called Bianchi. Bianchi, another Italian mathematician. Bianchi's second identity. This is a differential identity. The first identity is an algebraic identity. Okay, so if we write this and take the trace of if first we raise the index of in this Bianchi second identity and then take the trace twice, 2 times, we will get a new tensor. Of course, this involves Riemann curvature tensor, and we know that if we take the trace, it is converted into Ricci tensor, and if we take the trace, the Ricci tensor is converted into Ricci scalar. So this new tensor will be a combination of Ricci tensor and Ricci scalar, obviously, and this is given in equation 27. So equation 27 gives us a new tensor that we have denoted by GAB. Mostly it's denoted by this GAB. Some books write it as EAB also because it's called Einstein tensor. But GAB because it represents gravitation maybe. So it's mostly written as GAB. Now you see that the right hand side, both the tensors are symmetric. The Ricci tensor is symmetric, the metric tensor is symmetric, then obviously the left hand side is also symmetric. So this is a symmetric tensor, GAB, written as a combination of the Ricci tensor, the metric tensor, and the Ricci scalar. So GAB is equal to GBA, and it is also divergence free. This is a very useful property. The previous tensor, the stress energy tensor, is also divergence free, and this Einstein tensor is also divergence free. This is actually one of the important properties that help us, that motivate us to make these two tensors proportional. And this is actually what Einstein did. He wrote the Einstein tensor to be proportional to the matter tensor, the stress energy tensor. And when we do this, we get an equation which is called the Einstein field equation. I'm not going very fast. It's okay, huh? You're following me. I'm trying to be as simple as possible. So now we come to an important concept of these lectures, that GAB, the Einstein tensor, is proportional to TAB, the matter tensor. Okay, and GAB we just defined is actually, and if we replace this by some constant of proportionality, usually written by kappa, denoted by kappa in the books, this becomes an equation. which is called the Einstein field equation. If we write it in detail, AB minus R G AB R is equal to this constant into the AB. So these are called the Einstein field equations, the E, F, E. And some people say this is perhaps the most important equation written in the last century, given by Einstein in 1915. And in 2015, maybe you remember, the centennial was celebrated throughout the world, many events and conferences everywhere. And we also had one in the other university, a big conference. So this is perhaps the most important equation written in the last century. The subject of general relativity actually starts from here. This was the birth of this subject of general relativity, writing these equations. Now, there are many different aspects of these equations, the mathematical aspects, the physical aspects, and there are some philosophical aspects. People have written down articles and books on the philosophy of these equations and so on. And these lectures are basically about these equations and their solutions. So what this equation actually represents? You see that the left-hand side comes from the curvature, the Riemann curvature tensor, the Ricci tensor. So this is actually curvature or geometry. Geometry of the manifold. What is its curvature? What is the metric tensor that is defined on it? What manifold we are considering? What is the dimension of the manifold? What metric we are defining on that manifold? And right-hand side is matter. So it's actually an empirical relationship between geometry and matter, or people say mathematics and physics. All the concepts in mathematics, the manifold, its structure, everything, and the matter we are talking about, its energy, momentum, stress, and so on. All the properties are given on the right-hand side. So in philosophical discussion, some people even say that it combines imagination, our conceptual world, to the real world. So this is our conceptual world, the mathematical, and this is the real world. What is the content of the space, the manifold? The distribution and motion of matter. So this TAB actually, it's actually a generalization of the old stress energy tensor in elastodynamics and fluids and so on. You deal with the tensor that's the stress, that's called the stress tensor, sorry, the stress tensor with the dealing with the three-dimensional space. So this is actually generalization. It gives us the distribution and motion of matter. So how the matter is, what matter we are dealing with and how it is moving. By matter, you means whether we have a fluid or a solid. Even if it's a fluid, what is the relationship between the pressure and the density? Equation of state. What equation of state we are dealing with here, for example? Whether it's a perfect fluid or not. a non-perfect fluid, or ideal, a pressureless fluid, maybe, for example. We talk about dust, okay? So all kinds of matter have been studied here in this case. And then the other properties of matter, whether it's neutral or charged. If it is charged, what type of charge? It's only electrically charged or magnetically charged, or maybe some other charges also. So everything about, all information about the matter is contained in this TAB. So in four-dimensional space, you can realize that this TAB is actually a 4x4 matrix has 16 components, but it's symmetric. So there are 10 independent components. Yeah. So everything, all the information about the matter and its motion. So the energy and momentum. That's why I wrote its full name is stress energy momentum tensor. It gives you all information about the stresses, the energy, the momentum, everything is given. So all types of matter can come under this. And I told you that even if it's electrically charged or magnetically charged or whatever. And if they are moving, what type of motion? So that is also the information is in here. By different types of motion, I mean if it's a static, it's not moving at all. Motion is zero. If it's moving, then is it a rotation, a spin, or a translation? Moving in one direction, maybe axial direction or radial direction, whatever. Or maybe acceleration also. If it's moving in one radial direction, for example, is this motion with constant speed or variable speed? Is there any acceleration over there? And if it's spinning, is it spinning at a constant rate or a variable rate? Or there is an acceleration in spin also. So whatever you can think, whatever comes to your mind, actually can be represented here on the right hand side. So all the physical world, actual real world is on the right hand side, and all the curvature and geometrical properties, they are given on the left hand side. So this is actually a relationship, an empirical relationship between the real world and its geometrical properties over there. Actually, this equation in 1915 and its solution gave rise to whole new subjects in mathematics and physics. Like cosmology, as we understand, this application of this subject in physics, astrophysics and cosmology. So the cosmology that's developed after this equation, if we look at cosmology before this equation, it doesn't look like cosmology. There was no, it seems that there was no subject of cosmology in real terms before that. Everything started after these equations, from the solutions of these equations. And there's important branch of astrophysics, which is the relativistic astrophysics, which deals with some special objects. I will briefly talk about these things here. That also came from the solutions of these equations. So when we talk about the solutions of these equations, as we mentioned earlier, this is a highly non-linear, complicated equation. One thing you can easily guess that this is a symmetric. All the indices are symmetric. So this is symmetric equation. For example, if we have dimension 4. So whenever we talk about these equations of the solution, we need to fix some things, assume something. The first of them is what is the dimension we're talking about. So if we fix the dimension in 4, 5, there are other dimensions. People found the solution in the other dimensions also, 5, 6, so on. They're called higher dimension. And 3 and 2, they're called lower dimension. So people solve these equations in 3 and 2 also. but I will stick only to the 4-dimensional case in general relativity. So if the dimension is 4, and these are all tensors of rank 2, which means that we will have 10 independent components. So anything with 2 indices, and if it's symmetric, it has 10 independent components. Like a symmetric tensor, a symmetric matrix, 4 by 4 matrix, you have 10 independents. So these are actually number of equations. Number of equations is 10. So in 4-dimensional case, this is 10, and these are 10 equations. And then you select the coordinates. What coordinates you want to solve this in. Whether you're interested in Cartesian coordinates or spherical polar coordinates or some other coordinates. So you select the coordinates also. So you select things on the left-hand side and solve for all possible right-hand sides. This is one thing. Or you can assume, you can have some assumptions on the right-hand side and solve this. Now these are basically PDs, nonlinear PDs. So we can apply the techniques that we usually use in PDs to solve these equations. And these were written in 1915. And now after 107 years, the first solution came in 1916. And people are still solving these equations. It's unbelievable. For the last 107 years, people have been solving these equations. There are thousands of solutions. I mentioned the first book I mentioned, I think there's the exact solution of Einstein field equation. That's actually a catalog of thousands of solutions of these equations. And people are still, even today as we're talking, people are solving these equations. All the techniques that are available there for solving partial differential equations, people have used all those techniques. Then there are many techniques that they were developed only for the purpose of solving these equations. I mean, those whose main motivation was to solve these equations, they developed those techniques. They come up with new techniques for solving these equations. And they do it. The algebraic methods, group theoretic methods that are available in PDs, people have used those techniques also. Then numerical methods. The almost all numerical techniques people have used for the solution of these equations. And then there are special numerical or algebraic packages that have been developed just for solving Einstein field equation. Some of them are very famous, and these days they are developing. For example, the Einstein toolkit. Einstein toolkit that was developed a few years ago. At Caltech, perhaps. So that toolkit is used for solving these, for finding new solutions of these equations. Then there is another toolkit is called black hole perturbation toolkit. That is also used to obtain those solutions which are particularly of interest for studying black holes. So these are the different, toolkits that have been developed for the solution of these equations. So why do we want to solve these and what these solutions actually represent? So broadly speaking, we can say that those solutions have applications either in astrophysics and cosmology. And by astrophysics particularly, I mean the relativistic astrophysics. The subject of astrophysics actually existed before the Einstein field equations also. But there are some objects in this universe that can perhaps only be explained if we use these solutions of these equations. Then this subject is called relativistic asymptotic. And these objects are sometimes called compact objects. Actually, this course is basically on the mathematical properties, the application of symmetry method. But why those methods are important? I want to emphasize they're important because the solutions from these equations are important. And why the solutions are important, I want to just mention a few applications. So, because to give you the motivation that why this subject that we're talking about these lectures is important. Because the solution, we're talking about the classification of the solution. And why we study these solutions, because they have important applications. So the compact objects like white dwarfs, for example, like neutron stars, and finally the black holes. So these are called compact objects or dense objects. Actually, they can only properly be studied if we use general relativity, these equations. In fact, the existence of black holes is not possible without these equations. Black hole, as I mentioned in the book when we're talking about the book by Chandrasekhar in that book mentions that black holes are the simplest objects in this universe. Then he says that the only concept that are needed to construct a black hole are mathematical concepts. This is the simplest. We further say something philosophical about these objects also. He says that black hole is the only instance of a physical object that is completely described by mathematical equations. You know, we try to describe many objects and phenomena by mathematical equations, but we have to incorporate some simplifications and approximations and so on. Chandrasekhar says the black hole is the only object in this universe which can completely be described by mathematical equations. And we will come to that shortly. The black hole is just this surface and a point inside. I will talk about that later. So this important branch of astrophysics, which is called relativistic of astrophysics, this cannot be studied if we do not deal with these Einstein field equations. So this subject actually owe its existence to these field equations. Then the cosmology. I mentioned the subject of cosmology came into being after after we came up with some solutions of these equations that explain the whole universe. So when I say that this, we need to find some manifold with coordinates to start getting the solution. So what is the object before us? It can be Earth, for example. It can be sun, a star, okay? That will have some geometrical properties and some physical properties, okay? What are the contents and what is the distribution of motion of matter in that star or object or planet or whatever. So we can study those in this. And then we can take the whole universe as an object. If we take the whole universe as one entity and try to come up with a solution that explains everything about this universe, then the subject of cosmology comes into existence. So cosmology, basically modern cosmology, we can say, is the subject of studying those solutions of the field equations that describe the whole universe as a single entity. So of course, the different solutions and different models. The old and basic model was FRW Friedman Robertson Walker model of universe and so on. So now one of the most important branches in theoretical physics to study the cosmology. So what I wanted to emphasize is that some solutions can describe different objects in this universe, like stars and so on. Stars and it's different forms like neutron stars and black holes and so on. And some solutions describe the whole universe, the cosmology. So the importance of these solutions of this. And when we start with this, I said that we assume some symmetry also, like the dimension. It's been long. People have been saying that most of the objects in this universe are spherical in form. Most of these stars and other objects, they appear to be spherical. So therefore, spherical symmetry is intuitively the most common form where we solve these equations. So most of the solutions that we obtain are obtained in spherical symmetry. Even the universe can be approximated studied like a sphere, a big sphere. So the first solutions that came in 1916, and the solution we will be talking about some of the important solutions. They are solved in spherical symmetry here, and we assume a spherical symmetry and spherical coordinates. Therefore, the spherical coordinates, as mentioned earlier, P, R, theta, and phi, they will be used to obtain the solutions. Okay. So this constant of proportionality, I wrote kappa over there. And if we write this kappa in detail, it's actually 8 pi g over C4. Here G is the Newton's gravitation constant. That comes from the Newton's law of gravitation. C is the speed of light. And please note that this G with indices is the Einstein tensor. And this G without indices is the Newton's gravitation. It's a different object. It's not from this Einstein tensor. This is a Newton tensor. So these are all the terms. Oh, there is an extra term here. I forgot to mention that this Einstein field equation is sometimes written with an extra term here. Here, this is plus lambda GAV. And this is the form I've written in 30. This lambda is called cosmological constant. It is important when we are studying its cosmological solutions. Otherwise, this term is mostly taken to be equal to 0. In cosmology, this becomes very important. It's called cosmological constant. Whether the universe is expanding or contracting, or if it's expanding, how long it will go on expanding, so on. Other cases. For these questions, this term becomes important. But for the solution that we will be interested in, and the first solution that was written in 1916, we don't need this term, this extra term. Okay? And we just need this basic Einstein field equation. All the terms here are defined here. RAB is the Ricci tensor, R is the Ricci scalar, GAV is the metric tensor. Lambda is cosmological constant, G is Newton's gravitational constant, C is speed of light. and T is the energy momentum tensor. Now, as I mentioned earlier, sometimes we take C and G equal to 1. This is called gravitational units. And for analytical solutions, we usually ignore them. We take them equal to 1. They become important in when we are obtaining numerical solutions, but here we will mostly ignore them. Okay. So this 32 is the form of the Einstein field equation that I have written here. And when we say that we have to find out solution, what do we mean by solution? What is that quantity that we are interested in obtaining? So that quantity is actually the metric tensor G. You remember I write the metric tensor like this, the Riemann. So this is the line element or the solution. The solutions are the different names given to the solution. Some people call it the metric or line element or a space-time or even universe. Okay, so it depends on the application of that solution, what that represents. We give it a different name. Okay, so when we say that we're finding the solution, this means that we are interested in obtaining this line element, ds square. And here, as I mentioned, we'll be mostly dealing with 4-dimensional solutions. So line element with these indices A, B, with a range from 0, 1, 2, 3. Okay. So next we will be starting the discussion of the symmetries and the classification of these solutions and so on. So I think it will be a good idea if we stop. We have completed the first section, that why the solutions are important. I've tried to give you the motivation why these solutions are important, that why we will be dealing with their classification and symmetry properties. So I wanted to emphasize the importance of these solutions and how they are constructed, how the field equations are constructed. And the next the analysis of symmetries, and that will be talk about later. So if there are any, we should give them some time for the question, answer, or solution, and so on. Maybe I should go to the I should stop sharing and see if there are any chat. This is chat box. Okay, so they say that okay, they say this is very good and excellent. Okay, thank you. Yeah, we need these notes. Yes, I said I'm developing these notes, and I give them a final form, when I finish, then I make them available. So that is what they are saying, and I need these notes. I'm pleased to get the notes at this email. Okay, yeah, mostly people are talking about this excellent lecture. Okay, thank you very much. And yeah, this G is equal to 1, and this C is equal to 1. This is the gravitational units. And we will ignore analytic, as I mentioned earlier. I think this answers your question. That for analytical solutions, these are all constant, they don't play any role. When we solve analytically, so these are all this combination. Kappa is equal to this 8 pi G over C will be 4. They're constant, they don't play any role. So in numerical solutions, they become important. Yes.
You said that there are many solutions
Yes,
of
yeah.
the Einstein equation, and
Even today, people are solving, yes.
But why?
Why? Okay. So why people are still solving these?
Yeah, I mean, people change models. Or
Yes, for different models. Yes, you're right. For example, in cosmology, there are different models of the original, the very old model I talked about, the Friedman Robertson Walker, and then there was some modifications to that model. Then there was some other solutions that were obtained to describe this universe. And for other objects also, for example, the people originally solved this mostly for spheres, spherical objects. And then the people think that there are some objects which are not spherically symmetric. I will actually talk about some of these solutions that are not spherically symmetric. They are axially symmetric, or maybe cylinders, cylindrical solutions, and so on. Okay, so the reason for obtaining new solution is either you come up with a new manifold with different geometrical properties or new kind of matter. For example, somebody obtained a solution with some electric charge. Another person will come, if I want to incorporate magnetic charge also. So this will be a new object with both electric and magnetic charge. Or maybe no electric charge, only magnetically charged. And then the different types of magnetic charges. And then there are different types of charges apart from electrical and magnetic. There are other charges also. And so things go on. I will try to give you some examples of the solutions. Of course, we will not give all the derivation of the solutions here, but we will study some of the properties of the original solutions that were obtained. Okay, so he says that what Kirchhoff symbol become equal to, what does it mean? Equal to 2? I don't understand this. This he says it's a very informative lecture, and I want to ask how we calculate number of equations involved in EFEs. Okay, so number of equations. Yes, actually for all the tensors that I have written, so if an object is of rank 2 and it is symmetric, then the number of components is equal to n into n plus 1 over 2. This is the number of components for anything that is symmetric. So in Einstein field equation are symmetric, is 4-dimensional, so we get 10 equations. In 5 dimensions, it will be 15 equations. So this was the question, how do we calculate? So it's not about only the Einstein field equation, anything with 2 indices and symmetric, or the tensor, the Ricci tensor, the metric tensor, they will all have this formula for symmetric objects. And for anti-symmetric or skew symmetric, it is n into n minus 1 if it is something, because the diagonal becomes 0. Okay, so that was the last question. Where can I find the record? Okay, yeah. So mostly people are asking about the notes. So yes, they will become available as I complete them and finish them. That's all. Okay. Yeah. Yeah, they are. Yeah, they are with me, but
maybe me, like other people, want it from as far as you're going on.
okay, okay.
So that maybe they want to read before.
Okay, so in that is, I have not actually split them into different, but I will do something for that. Okay, yeah. Okay, yeah. Okay, thank you.
Thank you.